This is lecture 33A of Differential Equations in Linear Algebra. I said a few lectures ago that I thought I might be able to finish by about lecture 36. And for my students at Bethel University here in fall 2020 with COVID, it's been a difficult semester. I will end with lecture 36. But I'm starting to realize it's probably going to make a little bit more sense and be a little bit more complete of a course if I go to lecture 37 for future semesters at Bethel or for anybody else who's watching online. Here in lecture 33A, we're going to start by looking at an example of some strange behavior that can happen at non-hyperbolic equilibrium points. Hyperbolic equilibrium points are those for which the Hartman-Grobman theorem, linearization, works. All eigenvalues for the Jacobian matrix have non-zero real part. That is the nice case. But now we want to look at a not so nice case. Next, I'll review Hamiltonian and gradient systems on the plane. We've talked about that already, and the corresponding Hamiltonian and potential functions. Something new is called a Lyapunov function that we can apply to gradient systems, but we can also apply to non-gradient systems. In fact, we're going to apply it to an application ultimately, something called the unforced pendulum that swings back and forth with no external forcing, both in the quote-unquote ideal case with no damping and the realistic case with damping. All right, so let's look at page 1 of our example of what can happen at non-hyperbolic equilibrium points. We know the Hartman-Grobman theorem from a couple lectures ago gives no conclusion when the equilibrium point in question is non-hyperbolic, when the Jacobian matrix, the linearization, has at least one eigenvalue with zero real part. It could be the number 0, it could be a purely imaginary eigenvalue, which would come in actually pure imaginary complex conjugate pairs. So what happens in general? Various strange things can happen. Let's consider one example here. We're going to look at a one-parameter family of ODEs. It's going to be cubic in x and y, and there's going to be a parameter, mu. Here's the system. I've got x squared plus y squared kind of highlighted out in blue. The reason being is because it equals the square of the distance to the origin. In other words, it's the square of r, the polar coordinate, giving the distance to the origin. That's going to be important. What is the system? Well, of course, you can see it here. You can expand it out to this. You see it's cubic in both. You've got an x cubed term and an x times y squared term there. And down here, you have an x squared times y term there and a y cubed term there. The origin is an equilibrium point of the system for all values of mu, right? Plug in x equals 0, y equals 0. No matter what mu is, the right-hand sides are going to equal 0 there. dx dt and dy dt will be 0 at that point. The origin is going to be an equilibrium point. However, the Jacobian matrix evaluated at the origin is the same for all values of mu, and it equals this. It doesn't depend on mu. Right? You could do that just by thinking about throwing away the nonlinear terms, which is okay, because we are talking about linearizing at the origin. I could ignore those nonlinear terms. The right-hand side of the first equation would be y, the second would be negative x. You would get this matrix right here. Its trace is 0, its determinant is 0 minus negative 1, which is positive 1. In the trace determinant plane, it would be up on the positive d-axis. It would have purely imaginary eigenvalues. Okay? And therefore, the origin is non-hyperbolic, no matter what mu is. So what happens? The answer does depend on the value of mu. That does affect the system. But you can't predict what's going to happen from the Hartman-Grobman theorem. We can use Mathematica. Let's go ahead and do that now to see what happens. Okay, so here I have my right-hand side functions and my vector field. I'm defining those. And now we're just going to look at the stream plot. Here is what the stream plot is when mu is negative 1. What do we see? We see the origin as an equilibrium point. I could have drawn the null lines in here as well. I didn't bother, but I could have done that. We see solutions that do go toward the origin. It seems that the origin is a spiral sink. Although, if you look real close to the origin, they're not spiraling very rapidly. They are when you're far away from the origin, but when you're close, it's a very slow spiraling, and that actually is the case. What happens as mu increases? Well, when mu is negative, It's still a spiral sink, but the slow approach to the origin seems to be getting even slower and slower. In fact, you might be deceived into thinking maybe there's a periodic solution right there that's real close to the origin. But that would be wrong. When mu is 0, there are actually infinitely many periodic solutions. We have transitioned from a spiral sink with slow spiraling to, when mu is exactly 0, a center, an actual center. Not a spiral sink anymore. These actually are periodic solutions. The nonlinear terms, when mu is 0, actually do go away. You do get a linear system that has the origin as a center. But then when mu is positive, all of a sudden the origin becomes a spiral source. Solutions you can see are going away. Although when you're close, it looks like you could be deceived into thinking there's a periodic solution there. The spiraling away from the origin when mu is positive is fairly slow at first, then gets faster and faster. So do you understand what's going on here? The origin, again, is an equilibrium point for all values of mu. It's not hyperbolic. Non-hyperbolic no matter what mu is. We cannot apply the Hartman-Grobman theorem. We cannot apply linearization. And in fact, depending on the mu, you either get a spiral sink, a center, or a spiral source. Same Jacobian in all cases. Is there a way to understand why we are getting a spiral sink when mu is negative, and a spiral source when mu is positive, and in fact a center when mu is 0? We can confirm it symbolically by using a transformation to polar coordinates, which is actually a nonlinear transformation. We've talked a lot about linear transformations in this class, differential equations and linear algebra. Transformation to polar coordinates is nonlinear. What's the transformation? Well, if you know r and theta and you want to know x and y, through trigonometry, x equals r cos theta and y equals r sine theta. Now usually when you learn about that kind of thing in pre-calculus and calculus 1 or something, you just think of it as equations that tell you how to convert polar coordinates back to x and y. But you can think of this as a transformation from an r theta plane to an xy plane is perhaps the best way to do it. And for example, if r varied between 0 and 1, and theta bit varied between 0 and pi, for example, this rectangle right here would get mapped under this transformation to a half disk of radius 1 centered at the origin, theta going from 0 to pi. That's one way to imagine that as a transformation, a nonlinear transformation. Does it have an inverse transformation? Well, yes, though it's tricky. You can solve for r as the square root of x squared plus y squared. That's just the Pythagorean theorem. And you can solve for theta, sort of, by using the condition tangent theta is y over x. That will work as long as x is non-zero. So as long as you're not on the y-axis, this will convert back to theta when you take the inverse tangent and possibly add or subtract pi to it, because the inverse tangent gives you outputs between negative pi and positive pi. So if you're over in the second or third quadrant, you have to adjust. And again, if you're on the y-axis where x is 0, you have to adjust. So this is not a perfect way to think about it, but so you do have to be careful, but it is the basic idea. How can we use these equations? We can figure out what the new equations are in the new coordinates, the r theta coordinates. Before we were doing UV coordinates in linear algebra, but r and theta, r is the distance to the origin, theta is the angle with the positive x-axis, are polar coordinates. We can figure out what the new differential equations are in r and theta. It's a little tricky. Notice that I bold-faced some r's over there. That not bold-faced, but made them blue. That corresponds on the previous slide to the blue highlighting of x squared plus y squared, which equals r squared. And r itself is the square root of x squared plus y squared. So just double check all this. dr dt is the derivative with respect to t of this. Why? Because r equals the square root of x squared plus y squared. Again, that's the Pythagorean theorem. Okay, x and y depend on t. This does not differentiate to 0. We're thinking about differential equations. X and y are functions of t. So what does it differentiate to? Use the chain rule, bring down the 1/2 in front, subtract 1 from the exponent, then multiply times the derivative of the inside, x squared plus y squared, with respect to t, keeping in mind x and y both depend on t. I need the chain rule again. Or you actually could use the product rule too. X squared, its derivative with respect to t is 2x times dx dt. X does depend on t. I need the extra factor of dx dt. Similar kind of thing for dy dt. Now do a little bit of simplification. All the 2's cancel here, here, and here. 1 over x squared, square root of x squared plus y squared is the same as 1 over r. I can replace that with r on the bottom. I can replace dx dt with this because that was the dx dt equation from the previous slide. Notice the blue r squared, that corresponded to x squared plus y squared. And dy dt can be replaced by the right-hand side of the dy dt equation from the previous slide. It's not clear that this is helpful, but it actually is almost like magic. Stuff simplifies. The x times y there and the negative x times y there cancel. What you're left with is x times this plus y times that. There's a mu and an r squared common factor that can be factored out. Now I'm highlighting the r's in red. And then this is the same as r squared right here. R squared times r squared is r to the 4th. So it simplifies to mu r cubed for positive r at least, so we're not dividing by 0. It's maybe unclear what's going on when r is 0. We won't worry about it. That's the origin anyway. But what is that telling us? This is negative if mu is negative, 0 if mu is 0, and positive if mu is positive, because r cubed is positive when r is positive. What's that telling us? It's telling us the rate of change of the radial coordinate of along solution curves is negative when mu is negative, always, as long as r is positive. 0 when mu is 0, and positive when mu is positive. We do get a spiral sink when mu is negative. The point has to head toward the origin. It's not a proof, but we get a center when mu is 0, and we get a spiral source when mu is positive. R has to be an increasing function of t when mu is positive. Okay, that's nice. We also saw spiraling when theta was changing over time as well. Can we find a differential equation for theta? Take the derivative with respect to t of the inverse tangent of y over x. Implicitly assuming x is non-zero, we're not dividing by 0. This doesn't really define theta for theta between pi over 2 and 3 pi over 2, say. Don't worry about it. We're okay with this pseudo-derivation. What's the derivative of inverse tangent? It's 1 over 1 plus the input squared. The input is y over x, but then I need the chain rule. I need to differentiate y over x with respect to t, assuming both y and x depend on t. I need the quotient rule for that. Low is x, d high, derivative of high is dy dt. I'm looking at y over x there. Minus high, d low, the derivative of the bottom, of the top. Yeah, the bottom, which is x with respect to t. All over the low squared, bottom squared, x squared there. I can then distribute x squared through this. It becomes, after simplification, x squared plus y squared, our old friend, r squared, which I should have highlighted in blue, I guess. And what about the top? dy dt is this, just like it was up here. And dx dt is this, just like it was up here. And amazingly, again, stuff simplifies. In fact, a lot nicer even, to just -1 in this case. When r is positive, so we're not dividing by 0. In other words, theta is a decreasing function in time. In fact, it's a linearly decreasing function of time. The solutions spiral around the origin clockwise, because d theta dt is negative, at a constant angular velocity, you might say. -1 radian per unit of time. Yeah, this is confirming what we saw. It's not a proof, but it's confirming what we saw in the picture in Mathematica. Okay? So the moral of the story is lots of things can happen at non-equilibrium points. We can do even stranger examples. And sometimes you might be able to use polar coordinates to still understand what's going on. Sorry about the vacuuming. Happens every time here. Okay. Let's do our quick summary of what happens with Hamiltonian and gradient systems. My goal here is to get to the Lyapunov function idea and apply it to the pendulum, both the ideal and the realistic cases. No friction and friction. Of course, friction is realistic. This is very quick. I talked about this in lecture 32A. What is a Hamiltonian system and what are Hamiltonian functions? This is going to be very quick, but we will look at examples. Here's your general two-dimensional Hamiltonian system. dx dt is f is the partial of some function h with respect to y, and dy dt is g, which is the opposite of the partial derivative of that same function with respect to x. H is a function of x and y, and these are its partial derivatives. It's called the Hamiltonian function for the system. If you didn't know what h was, is there a way to tell whether a system is Hamiltonian or not? Yes. You would want to check and see, does the partial derivative of f, if you didn't know that it was Hamiltonian or not, does the partial derivative of f equal the opposite of the partial derivative of g with respect to y over the entire plane? Say we're assuming our domain is a plane, which keeps things simple. It's called a simply connected domain in particular. That makes these equivalent to each other. Why? Because if there is some Hamiltonian function, the partial of f with respect to x would be this mixed second order partial. Notational wise, this means differentiate h with respect to y first, then with respect to x you move from right to left. But when h is a nice enough function, c2, twice continuously differentiable, that second order mixed partial will equal this one. It's called Clairaut's theorem if you want to look it up. And that will equal, yes, the opposite of the partial of g with respect to y. These are equivalent conditions over the plane. What else did we learn? We also learned, because of this, it turns out that the derivative of h with respect to time along solution curves is always 0, no matter what solution curve you're talking about. We saw that. And that means solution curves lie on the level curves of h, curves in the plane where h is constant. In other words, h is a conserved quantity, kind of like conservation of energy. And in some problems, h really does represent conservation or energy, total mechanical energy, say, like for the ideal pendulum it will, or at least almost, up to a scalar multiple. It's conserved, it doesn't change over time. Cool. What about gradient systems and the corresponding potential functions? It's a very similar setup. dx dt is f is the partial of some function v with respect to x, and dy dt is g is the partial of that same function v with respect to y. And if you know about gradient vectors, put those two things in components of a vector, it's the gradient vector. If you want to think about gradient vectors, that can be helpful, but I'm not requiring my students to know about gradient vectors. I will briefly talk about how to interpret them visually, but they won't have to fully understand them. This is equivalent on the plane again, a simply connected domain, to this condition. Again, because the Clairaut's theorem right there. The partial of f with respect to the second variable y must equal the partial of g, the second right-hand side, with respect to the first variable over the entire plane. Okay? And once again, you can think about that as being a consequence of Clairaut's theorem. Just double checking that I didn't make a mistake. I think this is all good. And what do we learn about these systems? And v, by the way, is called a potential function, like potential energy, maybe. Maybe. Solution curves turn out to be orthogonal to the level curves of v. And in fact, this is actually something I did not mention in 32A. At each point in the plane, the rate of change, each non-equilibrium point, the rate of change of V is maximized in the direction of the given solution curve. So in other words, if this black curve is a level curve of V, it's a curve where V of x, y is some constant, call it C. A solution curve, and there'd be other level curves as well, but let's say this is a solution curve here. If it's going to cross V, it's got to cross with tangents that are at right angles to each other. Those two curves have to be orthogonal to each other, perpendicular. There's a right angle. And in fact, at that point right there, if you want to move in the direction that V increases fastest, maximize its rate of change, its derivative with respect to t in this case, or even with respect to the spatial coordinates, you got to go in that direction. In this picture, almost straight down like that. But it changes from point to point. Okay, this is calculus after all. And we are thinking about this for. And we'll see that in some pictures here shortly. Here's a new concept. For a gradient system with potential function V, the new function L, that is the opposite of V, is called a Lyapunov function for the system. It's got a new name, Lyapunov function. Now, I did mention in 32a that some people essentially take V to be the Lyapunov function at the beginning and say gradient systems have to have minus signs here and here to start with. Some people do that, and that makes some sense because when you talk about the gradient system this way, and you draw the contour map of V, a bunch of level curves, it's like the solution curves, if you're imagining them to be liquid, like liquid water, they'd have to flow uphill, so to speak. V increases. And it kind of makes more intuitive sense to want your solutions to flow downhill. So the level curves of L will be the same as the level curves of V, except the direction that the function increases will be the opposite. The values of L will be the opposite of the values of V. And also the direction they increase or decrease changes as well. Again, we'll see an example. What does it mean to be a Lyapunov function? It means the derivative along solution curves, along any non-equilibrium solution, this derivative is less than or equal to 0 for all t, again, along any non-equilibrium solution, with strict inequality, except for a discrete set of t's, like a finite set of t's, or what's called a countably infinite set of t's, like 1, 2, 3, 4, 5, 6, etc. That's what's called a discrete set of times. So you mostly have strict inequality for this derivative. What is this telling you? It's telling you the Lyapunov function is decreasing, for the most part, you might say, along solution curves. And when it has 0 rate of change, it's really only for a moment, so to speak, because of that discrete set of t's. Okay, I claim this is true, that this negative v is a potential function, or excuse me, a Lyapunov function for this. We should probably verify that quick with the multivariable calculus chain rule. Like we used with the Hamiltonian systems, what's the derivative of this Lyapunov function along the solution curve? I'm assuming x of t comma y of t is the solution curve. Well, it's the opposite of the derivative of the potential function because of how I've defined the Lyapunov function to be the opposite of the potential function. Now use the chain rule. That's the derivative of v with respect to x times dx dt, plus the derivative of v with respect to y times dy dt. Then use the differential equations. That's the same as dv dx. This is the same as dv dy. Or you could say partial of v with respect to x, partial of v with respect to y. So you really get the opposite of something that can't be negative. And these are not second derivatives, they are squares of first derivatives. dv dx squared plus dv dy squared. This certainly cannot be positive. This is less than or equal to 0 because of the negative sign there and because these are never negative. This is never positive. Does it equal 0, or excuse me, yeah, does it equal 0 only at a discrete set of t's? Well, that would depend on the rest of your setup, what the example is. So I guess I shouldn't say this is a theorem as I have it stated, but it usually happens, okay? We should really be more careful, but basically it does happen. That's always less than or equal to 0. Lyapunov functions can be used to define trapping regions for gradient systems. Remember I talked about trapping regions 2 lectures ago, I think, 31a. So I talked about it in the context of something called the Poincare-Bendixson theorem. That's coming back here a little bit now and also maybe the next lecture. Consider this example from lecture 32b. Actually, it was 32a, I believe. Okay, kind of a complicated looking system. It is a gradient system. I did come up with a potential function v that made these derivatives true. And you can solve for v by integration, though it's a little tricky. Complicated enough that I wouldn't want to do this without technology. To draw null lines, to draw level curves of v in this case. The potential function turned out to be that. You can double check by differentiating appropriately. Therefore, the Lyapunov function is the opposite of the potential function. Notice the signs are changing. It turns out, and I'm going to show you this on Mathematica here in a minute, that for any number c greater than or equal to approximately negative 8.49586, so I shouldn't say greater than or equal to. That's an approximation. The set S of c, defined by this equation, is a trapping region. This is the set of all points where the value of the Lyapunov function is less than or equal to c. It'll be more clear if we look at a picture. And what does it mean to be a trapping region? A couple lectures ago I said that that means that the time t flow map, the image of SC under the time t flow map, is a subset of itself. Some people assume it's a little bit more. They assume it's truly interior to the set, not touching the boundary, this image when t is positive. But this is going to be good enough for us. This is true for all non-negative t, assuming the flow maps are defined. And if it truly is a trapping region, it will be defined for all t, but I'm just sort of covering my bases there. So, visually, if this is S, what often happens with trapping regions, but not always, is your vector field points straight in along the boundary. So solutions that start on the boundary or inside stay inside for all t. The image of S under a time t flow map when t is positive could look like this. These are supposed to be filled in sets. The original I could have shaded, and this new one I could shade as well. The red set gets mapped to the green set. Think of it that way, the inner green set. Here's the theorem. Although I didn't state it correctly. If S is a trapping region, I meant to add a closed and bounded trapping region, also called compact. I will make the correction before I put this on the Google Drive. If S is a closed and bounded trapping region, closed means it contains its boundary. It's a little bit more technical than that, but that's good enough for us. Bounded means it doesn't go off to infinity in any direction. It's contained in some sufficiently large disk centered at the origin, say. If it's a closed and bounded trapping region for a flow on Rn, n can be any dimension, then there exists at least one solution that stays inside S for all times t, including negative times. That's the point. Like an equilibrium point, for example, or maybe a periodic solution, or maybe both. The Poincare-Bendixson theorem, I didn't put in the slide, but I'll remind you, said that if you've got a trapping region in the plane, n had to be 2, that contains no equilibrium points, it's got to have a periodic solution. That's a pretty significant thing. Although in such situations, the trapping region itself would have to be ring-shaped, typically. Otherwise, there'd be an equilibrium point in it as well if it wasn't ring-shaped. In higher dimensions, weird things can happen. The set of solutions that stay inside the trapping region for all time could be some strange object. In fact, they were even called strange attractors. What happens in our example? Let's look at Mathematica. Well, there's a picture from Mathematica. We'll also look at it again. I'm using, oops. Here we go. Here's the trapping region that's actually on the PowerPoint. It's this light blue region with the black boundary. I'm thinking of that black boundary as being part of the set. It's a closed and bounded set. You can see solutions go in. If they go in, they have to stay. And this is one of these sets S sub C for some C. In fact, how I programmed Mathematica to draw this is I picked C to be 5.2. C had to be greater than or equal to -8 something. I forgot what it was. What's the solution that stays inside for all t, or more than one solution actually? Well, the equilibrium points do, but also there are some separatrices between the equilibrium points. There's going to be one that goes from here to here about like this, so I can't draw in the Mathematica, I forgot. About like that. Try using this, I don't know if that works. A separatrix that goes about like that. Goes to that point as t goes to -infinity, and this point as t goes to +infinity. Another separatrix that goes from here to here, another one from here to here, and another one from there to there. Those 5 equilibria, along with those 4 separatrices, are going to be the solutions that stay inside the trapping region for all t. Not a periodic solution in this case. This shows we can let C change. It does change what the trapping region is, but there's still solutions that stay inside it for all t. If I do make C less than a certain amount, the trapping region breaks into 2 pieces. We've got 2 trapping regions now that only contain those 2 equilibrium points as solutions inside them for all t. But still, as long as C is bigger than -8 something, I forgot what it was, we will still get trapping regions here. Okay, they're getting smaller and smaller. Okay, and there's a static picture of our Mathematica. Let's apply this to the nonlinear unforced pendulum. Ideally, you'd spend, pun intended, ideally you'd spend more time here. I got to go kind of fast. We have talked about modeling masses on springs. This is analogous, not quite the same thing. Here's a picture of your general pendulum. It's a bob, a mass, on a rod, a thin rod that you unrealistically assume has no mass. Keeps the equation simpler if you assume the rod itself is somehow stiff but massless, even though that can't happen in real life. What are the forces acting on the mass? They're actually not all pictured here. There's the gravity force right there. There's also a force from the thin, stiff rod on the mass that might look about like this. The net force is the sum of the gravity force and this force from the rod. And that net force is indeed this thing right that you see there. That's the net force on the mass. And it's tangent to the curve of motion. The curve is always on a circle of radius L. And I am allowing for the bob to go around the horn here, so there's no ceiling at the top. If I give it a big enough initial velocity, or if I even position it up near the top to begin with. The only component of gravity that matters is the tangential component, tangent to the curve, this component right there. From trigonometry, you can get that. Its magnitude is mg sine theta, where g is the acceleration due to gravity. This angle is theta, this angle is also theta right there. And you can look at this right triangle there to figure that out. If we assume no friction, no damping, Newton's second law gives that right there. F equals ma, what's the force? It's this. Notice it's the opposite direction of the acceleration. Okay. Negative sign is needed. Think about why that's the case. Cancel the m's, divide both sides by g and rearrange, and you can write it this way. This is a nonlinear equation. Sine theta is your nonlinearity. It's not a nonlinearity in the independent variable t, which we do allow for linear equations. It's a nonlinearity in the dependent variable theta. By the way, when theta is close to 0, sine of theta is approximately equal to theta. So this equation, this second order nonlinear equation, can be approximated by a linear equation as long as theta is small. If the angle is small, the pendulum does act like a harmonic oscillator actually, but when the angle gets bigger, then strange things can happen because of that nonlinearity. We can convert this to a system. Let v be the angular velocity, d theta dt. So theta is in radians, say, t is in time, say, v would be in radians per second. The corresponding first order nonlinear system that I get by using that equation and also differentiating it with respect to t and solving this equation for that second derivative is this. d theta dt is v, that's the definition. dv dt is the second derivative of theta with respect to t twice, which again, if you solve for this, you get negative g over L sine theta. I went ahead and replaced g with 9.8 because I wanted to call the function g, not the same as the gravitational constant g. This system is Hamiltonian. The partial of the first right-hand side with respect to the first variable is the opposite of the partial of the second right-hand side with respect to the second variable. They're both always 0 over the entire plane. What's a Hamiltonian function? This. Integrate appropriately. This should be the partial of the Hamiltonian function with respect to the second variable, which is v. This is going to be dh dv. And this is going to be the opposite of the partial of h with respect to the first variable, which is theta. Theta is like the x, v is like the y here. Integrate appropriately, you'll get this. And certainly that seems kind of similar to kinetic energy. Yeah, and if m was 1, it would be kinetic energy. M doesn't really matter here, but it would matter for the actual kinetic energy. The energy is going to be a multiple of this, multiplied by m essentially. That's kinetic essentially up to a multiple of m. This minus 9.8 over L cos theta is actually potential energy, which you might wonder how can that have a minus sign. And well, sometimes you can take potentials to be negative in value. You can also add a constant on here to up its value if you only like positive values. But sometimes for the purpose of mathematical purposes, potentials can be negative. It's Hamiltonian. Solutions have to lie on the level curves. What do they look like here, though? Use technology. This is what they look like, at least when theta and v are both between negative 2 pi and positive 2 pi. I could extend it further, and the periodicity of sine of theta would actually mean this picture would periodically repeat itself, essentially. Which means, and maybe I'll talk about this in the next lecture, it might be better to not let the plane be your phase space. It might be better to let the phase space be a cylinder. I'll let you think about that. Solution curves have to lie on these. Thinking about the signs of d theta dt and dv dt, and then using technology to draw them, you see solution curves lying on those level curves. This picture, I noticed, is not perfect. That arrow there seems to be a numerical error or something. Mathematica just didn't draw it perfectly. There's another one right there. There could be some other ones like right there. Solutions in blue are supposed to be on the level curves. The origin is a center that corresponds to back and forth motion. This point here is a saddle point. What does that correspond to? That's where theta is pi. Here's theta 0. Theta is pi. 180 degrees is straight up. Would you ever observe a pendulum sticking straight up for more than a millisecond? No, you wouldn't in real life. It would start moving because you're not going to be perfectly at equilibrium. It's a saddle point. It's unstable in a sense. You can't actually observe this equilibrium point in real life, but it does exist mathematically speaking. There are separatrices. In fact, there's one going from about here to there. Didn't draw it perfectly. What does that represent? That represents, oh, your mass is just barely past the equilibrium point here, but it was really close. And then all of a sudden it goes like that, and it comes back really close to where it started, and it never comes back down either. You'd never observe that either in real life. There are also solution curves that go up and down like that. In the absence of friction, if you gave the pendulum enough initial velocity, it would keep going around and around and around, faster at the bottom, slower at the top, like that. As t increases, that's what those represent. Not observable physically, but interesting to think about mathematically. What about the realistic case? So now we're adding damping, in other words, friction. How should we do that? Keep it simple, like we did with harmonic oscillators. Make the friction, the damping, directly proportional to the velocity. Now the actual velocity is not d theta dt. The actual velocity is L times d theta dt. We want to get rid of the L though, or at least deal with it in a way that makes it nice, I guess I should say. So here's your force due to gravity. Here's your force due to friction. Notice the extra factor of L in there. And yeah, I needed the extra factor of L here too. Divide both sides by L. Also divide both sides by M. Rearrange, you can write it this way. We still have our nonlinearity right there. I'm not going to do it in this lecture, but you may want to think about the equilibrium points in these problems and using a Jacobian matrix to linearize near them, though technically it doesn't apply. The Hartman-Grobman theorem doesn't apply when the origin is a center or some other point is a center. It was a Hamiltonian system in the ideal case anyway, so it was a center because the level curves had to come back to where they start. They had to be closed curves. Once again, we can let v be the angular velocity. The corresponding first order system is this. Sad, 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 this is no longer Hamiltonian. If v is positive. The partial of the first right-hand side with respect to the first variable is always 0, but the partial of the second right-hand side with respect to the second variable, and then including a minus sign, gives us, so there's a typo here, not b over L, but b over m. Differentiate this with respect to v, then put a minus sign. The minus sign goes away, you get b over m. It's non-zero. It's not Hamiltonian. Is it gradient? No, it's not gradient either. However, the opposite of the energy function, the Hamiltonian function for the ideal case, can be used as a Lyapunov function. I won't verify that. Take the time to verify it. Maybe you want to do it as an exercise. Differentiate this along a solution curve. Maybe I'll do it in the next lecture, but in between you can do it for yourself. Differentiate this with respect to t along a solution curve. Replace theta with theta of t, v with v of t. Use the chain rule. You should get something that's always less than or equal to 0. Notice the negative sign there and the plus sign there. That's the opposite signs of the Hamiltonian function from the other example, the ideal case. Is it only equal to 0 at a discrete set of t's? Well, we don't need to prove that, but we can see in the picture that it seems right. And in fact, what does the picture look like? Here we now have the level curves of not the Hamiltonian function, but the Lyapunov function. But wait a minute. Doesn't that look the same as the Hamiltonian one? Actually, it's not. The curves are the same, but the values are different, and the shading is different. With the Hamiltonian, it was darker near the origin and lighter as you went away. Here, it's lighter and darker as you go away. The Lyapunov function is the opposite of the Hamiltonian function. That's why. In solutions, actually, I'm realizing I might have made another mistake here. Solutions should decrease along the Lyapunov function, so Maybe I should have just done the Hamiltonian. I'll have to think about that. I'll put a little note on the video about whether that's right or not. Because solutions end up looking like this, and they actually do increase along the Lyapunov function. I think this Lyapunov function, I think the Lyapunov function actually does have to be the Hamiltonian function to make sure the derivative is always negative. And that makes sense too if you think of the Hamiltonian function as being a constant multiple of the total energy. The energy is going to decrease, dissipate. Mechanical energy I'm talking about. Energy is dissipating mechanically with regard to motion. It is still being conserved overall, transferred to being heat, maybe, you know, as it slows down. It is heating up the air molecules, you might say, from its actual motion. So it's losing energy because of that, and because of energy in the attachment of the rod to wherever it's attached. It's losing some energy there too. But notice solution curves are going, they're crossing the level curves, not orthogonally. This is not a gradient system, but they are going across them. And yeah, if I let L be H itself, they'd be going toward decreasing energy levels. The origin now becomes a spiral sink. That corresponds to motion that while it swings back and forth, the amplitude gets smaller and smaller over time. That's what that corresponds to. And notice the Nelk lines are in here too, and the V Nelk line changed from being vertical lines to being sort of a sinusoid here, it looks like, which makes sense if you think about the equations themselves. Let's end lecture 33A by going to Mathematica again quick. Now we're looking at the pendulum. This is code to approximate the solution and see it. This is the undamped ideal case. You see the pendulum swinging back and forth as you would expect. We can see how that looks when you compare it to the phase plane. The actual motion on the left and the phase plane solution curve on the right. You should think about the relationship between these two pictures and how the theta and v coordinates of the red dot on the right are telling you the position, angular position and angular velocity on the left. We can also graph theta and v as functions of time. And though they don't look like cosines and sines, they have some similarities. We can also add friction. Here is the solution curves we just saw, and now let's look at, oh, no, this is still the undamped case, sorry. All right, enter all these things. Now we are in the damped case. Actually, this is still undamped because I set b to be 0, but if I add some damping, I can also change my initial angle and my initial angular velocity if I like. Now let time go by. Now the solution is heading toward the origin. The motion is getting smaller and smaller in amplitude over time. If I make the damping higher, the effect gets more pronounced. You can see it approaching equilibrium pretty fast. That's the end of lecture 33A. Thanks for watching.